Now, in part 3, we aim at dealing with the main results of this presentation, which is existence of free boundary minimal surfaces of any finite topology into some Euclidean ball. This will be proved by maximization of the first Steklov eigenvalue. That's why I talk about shape optimization. And in this picture, you can see examples of free boundary minimal surfaces obtained by maximization of the first non-zero Steklov eigenvalue. It is what did Cao, Hosting, and Ude by numerical computations. So here you have genus zero surfaces with some boundary components, 3 here, 5 here, etc. So let's look for these surfaces by theoretical techniques. So let me recall what the Dirichlet-Neumann operator and Steklov eigenvalues are. On a surface without boundary, with a boundary, we have a characterization by the genus and the number of boundary components of the topology. These two numbers characterize the topology of such a surface. And since it is a Riemannian surface, we have some operators associated to the metric, the Laplace operator, for instance, and the Dirichlet-Neumann operator associated to this Laplace operator. So it is defined the following way. You take a function on the boundary and you associate the normal derivative of its harmonic extension. So the harmonic extension of u is just a harmonic function which is equal to u at the boundary, and d nu is the outward pointing normal derivative with respect to the metric g. This operator behaves like the Laplacian. It is self-adjoint, and it is also a pseudo-differential operator of order 1. But since the surface is compact, like for the Laplacian, we have a sequence of eigenvalues which represents the spectrum. The first eigenvalue is equal to 0. It is associated to constant functions. And the other ones are positive because we are on a connected surface. And they go to plus infinity as the index goes to plus infinity. We have a variational characterization of Steklov eigenvalue, like for the Laplacian. And notice that the difference with the Laplacian is that the denominator is here an integral on the boundary of the surface. But the analysis will be very similar to the analysis on the Laplacian. We will have some elliptic equation, and we can use elliptic regularity theory at the boundary. So the function is harmonic on the surface, and you have this relation between d nu u and u by d nu u equals to sigma u here. So this is the equation for eigenfunction. Okay, so why are we interested in this Steklov eigenvalue? It's because if we look for critical metrics for Steklov eigenvalues, so G is a critical metric in this theorem with fixed length equal to 1, then there is some integer and a map into Rp and into a ball a posteriori, such that the coordinate function of u are eigenfunction associated to the kth Steklov eigenvalue here, and the boundary is sent into a sphere by the map. So both properties give you that the map U is a free boundary harmonic map. The last condition is given because thanks to the Euler-Lagrange equation again, we also have conformality for the map U. So if it is harmonic and conformal, it is then minimal, and we obtain a minimal immersion with free boundary. Moreover, we have a characterization of the critical metric. It is the induced metric of the immersion up to a conformal factor equal to 1, because if you look at the Rayleigh quotients characterizing the eigenvalues, the numerator is conformal invariance in dimension 2, it is the Dirichlet energy, and the denominator only depends on the conformal factor on the boundary. So that if we do not change the conformal factor at the boundary, the Steklov eigenvalue will be the same. That's why it's up to conformal factor equal to 1. It's somewhat Steklov isometric. Fraser and Shane discovered this theorem, but they also discovered that if we do a variational problem in a fixed conformal class, we also have characterization of critical metrics by the two first properties in this theorem, that you have a map such that the coordinate functions are eigenfunctions associated to the case Steklov eigenvalue, and the boundary is sent into a sphere. But we do not have the conformality because the space of variation is much smaller than for the first theorem. Here we also have a characterization of the metric by a conformal factor times a reference metric here, such that the conformal factor at the boundary is equal to something depending on the map. And it is somewhat a density of energy on the boundary. Fraser and Shane were inspired by Nadirashvili and Sophie Elias for their theorem. I just recall them quickly. In the closed case, on a closed surface, if we take a metric which is critical for the case Laplace eigenvalue times the area, then, as previously, we have the two first properties which give you that you are a harmonic map. If we do variation in a fixed conformal class, you obtain a harmonic map. And because you do variation in all the metric space, you also have conformality, so that U is a minimal immersion into some sphere. And we also have a characterization of the critical metric, just the induced metric of the minimal immersion. And again, if you are in a fixed conformal class, we do not have the last result, but we still have that it is a harmonic map into some sphere, and the metric is characterized by the map and a reference metric, and the conformal factor here is just the density of energy of the harmonic map. Okay, so let's give a short proof of this result, which is simpler to prove than the previous results, but the spirit is the same for all the other results. So for that, for this sketch of proof, I give a definition of being critical. So here, notice that the eigenvalues are not smooth, because we denote the eigenvalues as a sequence counted with multiplicity. So that when we have multiplicity, we have that the branch of the first eigenvalue, for instance, is this one, and the second eigenvalue is this one. So that you have a corner here, and it is not a smooth map with respect to the metric. And we expect that the metric are multiple when they are critical, so that we cannot perform a variational problem for a smooth functional. We have to do it for a functional which is non-smooth. And a convenient definition for being critical in this case is that if we take the left derivative and the right derivative, then they do not have the same sign. And we do it for any variation of the metric. So if we are in a conformal constraint case, you just use variation in the conformal class. That's why I take 1 plus TV as a variation. And the assumption is that this is negative. So all we need is to compute the left derivative and the right derivative. Right derivative, left derivative. To simplify, we compute it for the first eigenvalue, but for the other one, it's the same technique. And we aim at proving that if we take a variation, a small variation of the metric of this form, 1 plus TV times G, we would like to prove that the right derivative is the infimum of this quantity, and the left derivative is the supremum of this quantity, infimum and supremum taken over the set of first eigenfunction with L2 norm equal to 1. So we find that if the multiplicity of the first eigenvalue is equal to 1, then the left derivative and the right derivative are equal. It's because it's a branch of eigenfunction, which is smooth. But when it is multiple, this quantity may be different. And we expect that for critical metrics, they always have different signs. So let us compute these quantities. So first, we aim at proving that the sequence of eigenvalues associated to this variation converges to the eigenvalue as t goes to 0. So it is the zero order term for the Taylor extension of the eigenvalue. But for that, we can prove equalities in two sides. The first side is because we can use the first eigenfunction on a fixed surface with a fixed metric as a test function for the variational characterization of the first eigenfunction for the new surface with metric GT. And when we do it, we have this inequality, and we can compute so that by an extension with respect to t as t goes to 0, we have this inequality. So we have a zero order term and a first order term, and we find this term as being somewhat the derivative of the eigenvalue. It is the term we had before, and we would like to have when we compute the derivative. Then, looking at lambda t minus lambda divided by t, the variation of lambda, and passing to the infimum when t is positive and supremum where t is negative, we obtain these inequalities. So when t is positive, when you divide, the inequality is the same here. And when t is negative, the inequality changes the side so that you have these inequalities passing to the infimum and supremum. And the difficulty of this is to prove that, in fact, actually you have equality here. And for that, we have to deal with the equation satisfied by first eigenfunction on the surface sigma t, sigma endowed with the metric gt. So let's take the first eigenfunction here. We assume that with respect to the metric gt, the first eigenfunction is normalized, has norm equal to 1. And we would like to compute the expansions as t go to 0 of the first eigenvalue and the first eigenfunction. So the ansatz is the following. We have the first variation lambda naught and lambda dot and phi dot as t goes to 0. And in particular, we would like to obtain lambda dot. So lambda t is bounded by lambda plus something which is of order of t. So up to the extraction of the subsequence, we know that lambda t goes to nu as t goes to 0, and nu is less than lambda. It's the first thing to do. We want to prove that lambda t converges to lambda. But by elliptic theory, we know that this converges as t goes to 0 to some equation, Laplace g phi equal to nu phi, where phi is the limit of phi t, thanks to standard elliptic theory, because we have a priori estimates on these eigenfunctions. And then we know, since phi t converges with respect to any function space to phi, we know that the norm of phi, the L2 norm is equal to 1, and phi is orthogonal to the constant function, because it was the case before the limits. So that we cannot have that phi is the constant function, and phi is an eigenfunction associated to the metric G. Since it is less than the first eigenvalue, we must have that nu is equal to lambda. And this means that phi is the first eigenfunction associated to the metric G. So this is computation for the 0 order term. Then we want to do computation for the first order term. So we have to deal with phi t minus somewhat the limit of phi t, and pass to the limit on it. So instead of taking the limit of phi t, we take the projection on the first eigenspace associated to the metric G of phi t. Then it is easy to see that we have this equation on the rest, RT. And to deal with elliptic theory, we set all the norms that are useful for us to see the good scaling for this equation. And we look at the infinity norm of RT, the difference between lambda t and lambda, and t. So we'd like to prove that alpha t has the same scale as t. And dividing by alpha t, it is clear that up to the extraction of the subsequence as t goes to 0, this quantity converges to something, and this quantity converges to something. So this thing is somewhat the variation of the first eigenvalue. And by standard elliptic theory, if we divide by alpha t the equation, then we find that RT converges, RT dividing by alpha t, converges in any function space, for instance, in C2, to some function R star. And at the limit, we have an equation. We obtain that R star, Laplace G R star minus lambda R star is equal to this quantity. And we also obtain that since we divided by alpha t everything, that 1 is equal to the sum of these quantities. So now let's argue with these equations. we integrate the equation against phi, which is the first limiting eigenfunction in our problem. Then we have that delta star is equal to something depending on t star. And if t star is equal to 0, then delta star is equal to 0, thanks to this equation. And then we obtain, thanks to this equation, that r star is a first eigenfunction. But by assumption, we had before the limit that RT were orthogonal to the first eigenspace, so that R star is also orthogonal to the space of first eigenfunction. Then, if it satisfies this equation, we must have that R star is equal to 0. But since everything is equal to 0, we have 1 equal to 0, and it is a contradiction. Therefore, we must have that T star is non-zero. And if we compute the variation of lambda, we obtain that dividing by alpha t and multiplying by alpha t in each side, and knowing that T star is different to 0, we obtain exactly what we expected. We obtain that the infimum and the supremum in the previous part, in the previous slides, are realized by some eigenfunction. Therefore, we have equality. Now, by assumption, since we have a critical metric, we obtain this. We have to multiply by the length, by the area of the surface. So the area is nothing but 1 plus t times the integral of the variation. And we have to use that. The metric is critical with respect to this variation. And when we come to the derivative, we have that this is negative. And therefore, this means that for any variation, we have a first eigenfunction such that this quantity is equal to 0, because the supremum and the infimum have different signs. And then, by a classical separation theorem, it is easy to see that we cannot have that the intersection here is empty. So it is non-empty. And then, where here is the convex hull of this set, and then we have that 0 belongs to the convex hull of this set. This means that you have a map with some eigenfunctions such that such that phi squared, the L2 norm of this map is equal to 1, and we get the theorem in the conformal constraint case. Okay, so now let's deal with the results. We had a characterization of maximal metrics for the first Tekloff eigenvalue. And here, thanks to this characterization, we are able to prove with Henrik Mathiesen that if we have a compact connective surface with some boundary, then there is a possibly branched minimal immersion with free boundary U sigma into some ball. So let me give some remarks. First, this theorem is true for any finite topology, including the non-orientable cases. We also have that the integer p sigma is lower than the multiplicity of the first Tekloff eigenvalue associated to the critical metric, so that the multiplicity is so that P sigma is controlled by the topology, because the multiplicity is controlled by the topology of sigma in dimension 2. For instance, for zero genus surfaces, we can prove that the multiplicity is bounded by 3. And moreover, Fraser and Shane proved that if we have 3 boundary minimal surfaces into a ball, a Euclidean ball, which is with respect to the first Steklov eigenvalue, then it is embedded. So you have, thanks to this result, 3 boundary minimal surfaces which are embedded into some 3-dimensional ball for any zero genus surfaces. And finally, we will be able to prove that for any fixed genuses, if we take a 3 boundary minimal surface S, then there is at most a finite number of boundary components such that the associated minimal immersion of this theorem are branch cover over S. So it is very rare to have a branch cover over some surface. So we can rule out branch points at some point. And moreover, we have that P sigma is in fact greater than 3. We do not have branch cover over the disk, for instance. So I will explain why we have this result at the end of this part. And of course, this result is the consequence, a direct consequence of the maximization of the first Steklov eigenvalue. So if we take a surface which is compact connected with some boundary, then there is a smooth metric maximizing the first Steklov eigenvalue. So how to prove this kind of theorem? There is a first result we need. And to state this result, we need to define the supremum over all the metric of the first Steklov eigenvalue on a fixed compact oriented connected surface, for instance, oriented to simplify. We can do it also for non-oriented surfaces. And this quantity is a topological invariant depending on the genus and on the number of boundary components. And the following theorem states that if we have these strict inequalities, then there is a smooth metric maximizing this functional for surfaces of genus gamma with m boundary components. So in some sense, if you have strict inequality with respect to lower topologies, then you have a smooth metric maximizing this functional. And then you have these 3 boundary minimal immersions. So we reduce the problem to finding, to proving this gap here, this spectral gap. So one remark is that the large inequalities are very easy to prove. Let me give you a sketch, a drawing for it. So to prove this kind of result, what we do, we take a surface for the first strict inequality, for instance, this one. We take a surface sigma of genus gamma minus 1 with m plus 1 boundary components. And we attach to this surface a strip along the boundary. And we assume that this strip is very small in some sense. For instance, the length of this strip is small. And if we take a metric which is almost maximal for this variational characterization on the surface sigma, and if we add this strip, then we have a new surface of genus gamma with M boundary components with a new metric, which is in some sense close to the previous one. Then we can test this metric for this variational characterization so that we have a kind of large inequality up to an error term. And then letting the size of this thing go to 0, the error term disappear at the limit, and we have this kind of large inequality at the limit. The argument is the same for this strict inequality, but in this case, we attach the strip on a same boundary component. Because here we lose, we win a boundary component, but we do not win any genus in this case. So starting with a surface of genus gamma with m-1 boundary components. We can also do this strict inequality by another method. You take your surface, to not the strict but the large inequality, and you rule out some disk with very small radius, and you let the radius go to 0. And in some sense, you change the topology as here, and you have the large inequality at the limit. And you can also do it by gluing this strip in a non-orientable way, so that you have large inequalities for any kind of topology. But what this theorem tells you that if we are far from being if the first eigenvalue is very far from the first eigenvalue of lower topologies, we cannot have degenerescence of maximizing sequence in some sense. You have compactness. The only non-compactness happens when these quantities are equal. This is exactly what this theorem tells you. So let me give a short explanation on this theorem. So the strategy is in 2 steps. The first step is by assuming that there is a maximizing sequence of metric which are maximal in their conformal classes. So in the following step, I shall detail after, we build a maximizing sequence of metric Gn, which are maximal for this functional in a fixed conformal class, for metrics lying in the conformal class of Gn. Then we can write Gn as a conformal factor times some hyperbolic metric, such that the boundary of the surface is a geodesic. And we have several tools when we have this kind of sequence. First, we notice that since the sequence of metric are maximal for the conformal constraint problem, then you have a sequence of free boundary harmonic maps associated to the first Steklov eigenvalue. Therefore, e to the 2un is connected to the map, the free boundary harmonic map. At the boundary, we have a relation with some density of energy of this map, so that we have to deal with sequences of free boundary harmonic maps. And we can prove that the only non-compactness for this kind of sequences is bubbles. So we have to rule out bubbles. Then we have another tool, which is Dulling-Mumford compactification for sequence of hyperbolic metrics. So we have to deal with the sequence of Hn, and the only non-compactness that can happen is that we have some maybe closed geodesics or geodesics connecting boundary components which shrink as n goes to plus infinity. And in this case, we can study the behavior of the metric at the neighborhood of these shrinking geodesics by some Collar lemma. And thanks to these tools, we are able to say that by the gap assumptions, we can rule out the only possible degenerations are as n go to plus infinity. The first degeneration are bubbles for free boundary harmonic maps here, and the other ones are degenerations for conformal classes. These cannot happen because, for instance, because we are a maximizing sequence, we cannot have disconnected surfaces at the limit. This is the idea. So that we must have only one thick part, only one part which has all the mass. For instance, the mass is on bubbles or on a connected component at the limit when we do the Lin-Montfort compactification, or in the collars. But in all these cases, it is not possible because we have the gap assumption. And we cannot degenerate to lower topologies. Therefore, thanks to the gap assumption, we have the theorem. But we have to prove in step 2 that there are maximizers in a fixed conformal class. So this problem is somewhat simpler because we maximize the Steklov eigenvalue only on a set of functions. And moreover, since we have conformal invariance of the Dirichlet energy, it's just on a set of functions on the boundary. So we would like to maximize this quantity, the first Steklov eigenvalue times the length of the boundary. And the natural variational space for this problem is the set of probability measures, because any maximizing sequence of metric of length 1 has this property, the L1 norm of the control factor equal to 1. And this means that e to the un weak star converges to some measure. So why do we do this? Because in variational problems, we would like to follow a classical scheme, which is we take a maximizing sequence of functions. We let them converge in a big space, here the space of measures, and we expect that at the limits, we can formulate Euler-Lagrange equations so that we can prove regularity and go back to the previous space, the space of smooth functions. It's a classical way to argue in variational problems. But here, we have a good thing which is that the first Steklov eigenvalue is upper semi-continuous with respect to the sequence here, so that this has to be maximal. And if we prove that nu is regular, that is that it is equal to smooth functions times the volume associated to the metric, then it is okay. But we cannot compute any Euler-Lagrange equation with respect to this measure. Because as you saw before, Euler-Lagrange equation begins like there are eigenfunctions such that blah, blah, blah. But here, we do not have any eigenfunction associated to measures. We can define eigenvalues, but we cannot prove that this infimum is realized when we replace e to the u by some measure. So we have a problem here. The idea to deal with this problem is to build a maximizing sequence of metrics which are maximal for some regularized variational problem, so that we have Euler-Lagrange equation associated to this maximizing sequence of metric, and we can deal with a sequence of function having some kind of pseudo harmonic maps, in fact, as n goes to plus infinity. So we renounce to choose any sequence of metric, but we build a specific sequence of metric. Okay, so I stop here for these results. And now let me state the main results that I will prove. I will give sketch of proof in the next part. It is that if you take a surface, a Riemannian surface with some boundary, and if we assume that we have a surface topologically obtained from sigma by attaching two opposite sides of the boundary of a strip along two disjoint portions of the boundary of sigma, then there is a smooth metric G tilde and sigma tilde such that we have the strict inequality. Therefore, thanks to these results, we are able to use this theorem and this theorem in order to prove in the same proof that we have strict inequalities and we have a maximal metric for this functional. So we prove it by induction. We start with the disk, for instance, which has a maximizer by classical result by Weinstock. The maximizer is a flat disk. So you start with the flat disk. You glue on this flat disk a strip along the boundary of the disk, and we obtain a surface with two boundary components. It is like an annulus. And we take the metric G tilde on this annulus given by this theorem, such that we have this strict inequality. Then, thanks to this theorem, we have strict inequalities, and then we have a smooth metric maximizing the first Tekloff eigenvalue on the annulus. And we continue. We attach a strip on the annulus. If we attach the strip on a same boundary component, then we increase the number of boundary components. We have the surface of genus 0 with three boundary components. And we do the same thing. We apply this theorem and then this theorem. And if we attach it in two different boundary components, then we increase the genus and decrease the number of boundary components. And so on. By induction, we deduce everything. Moreover, thanks to this theorem, we're able to prove that the minimal immersion obtained by maximizing the first Tekloff eigenvalue cannot have branch points in many cases. Indeed, if you take a surface of fixed genus, positive genus, we know that the first non-zero Tekloff eigenvalue and the supremum of this eigenvalue is controlled only by a number depending on the genus. Therefore, if you denote J the number of boundary components such that the maximizer are branch covered over free boundary minimal surface S, then we know that by isoperimetric inequality that the added length has to be at least 2 pi, so that the gap gives you that the gap is 2 pi when we have branch covers, at least 2 pi. And then, since we have a upper bound not depending on the number of boundary components, we obtain that this number J is controlled. And there is only a finite number of branch covers. So in the next part, I will deal with the proof of this theorem.